Hi, hello there. Welcome to Routing Concepts. No matter how effectively you set up your network, something will always stop working correctly, or even stop working completely. This is a simple truth about networking. So, even though you already know quite a bit about routing, you still need to know how your routers actually work. So, this knowledge is critical if you want to be able to troubleshoot your network. So this module goes into detail about the functions of a router. So let's get started. So for the module objective, at the end of this video lecture, you should be able to explain how routers use information in packets to make forwarding decisions. Also included on this video lecture are subtopics like path determination, packet forwarding, basic router configuration review, IP routing, and the static and dynamic routing. So let's begin with path determination. Okay, so there are two basic functions of a router. So before a router forwards a packet anywhere, it has to determine the best path for the packet to take. So this topic explains how routers make this determination. So Ethernet switches are used to connect end devices and other intermediary devices, such as other Ethernet switch or switches, to the same network. So some connects multiple networks. So like routers. A router connects multiple networks, which means that it has multiple interfaces that it's going to the different IP network. So when a router receives an IP packet on one interface, it determines which interface to use to forward the packet to the destination. So this is known as routing. So the interface that the router uses to forward a packet may be the final destination, or it may be the network connected to another router that is used to reach the destination network. So each network that the router connects to typically requires a separate interface, but this may not always be the case. The primary functions of a router are first, to determine the best path to forward packets based on the information in its routing table, and second, to forward packets toward their destination. Now I have here an example, router functions example. So the router uses its IP routing table to determine which path or route to use to forward the packet. So R1 and R2 use their respective IP routing table to first determine the best path and then forward the packet. So initially, we have here the source, and the destination. So the source will forward the packet to the router. The router will refer to the routing table if it has an entry on it. And then, if there is an entry, it will be forwarded to the exit interface leading to another network or router. In that case, that is router 2. Router 2 will process the packet and do the same as that of router 1, referring to the routing table. Then it will be forwarded to the destination. So that's how it works. Router always refer to its routing table where to forward the packet. Now, if there is no entry for the router, for that packet, then the router will simply drop the packet. Unless there is a configuration or there were configurations like the gateway of last resort where to forward the packet not found on the routing table. Alright, so the next one would be the best path equal longest match. So what is meant by the router must determine the best path in the routing table. So the best path in the routing table is also known as the longest match. So the longest match is a process the router uses to find a match between the destination IP address of the packet and a routing entry in the routing table. So the routing table contains route entries consisting of a prefix or network address and prefix length. So for there to be a match between the destination IP address of a packet and a route in the routing table, a minimum number of far left bits must match between the IP address of the packet and the route in the routing table. So the prefix length of the route in the routing table is used to determine the minimum number of far left bits that must match. Remember that in IP packet, only contains the destination IP address and not the prefix length. So the longest match is the route in the routing table that has the greatest number of far left matching bits with the destination IP address on the packet. So the route with the greatest number of equivalent far left bits, or the longest match, is always the preferred route. So take note, the term prefix length will be used to refer to the network portion for both IPv4 and IPv6 IP addresses. So IPv4 address longest match example here. Now in the table, an IPv4 packet has a destination IP address or IPv4 address of 172.16.0.10. So the router has 3 route entries in its IPv4 routing table that matches this packet. So these are 172.16.00/12, 172.16.00/18, and 172.16.00/26. So of the 3 routes, 172.16.00/26 has the longest match and would be chosen to forward the packet. So remember, for any of these routes to be considered a match, there must be at least the number of matching bits indicated by the subnet mask for the route. So let's have an example for IPv6. IPv6 address longest match. Now in the table, an IPv6 packet has a destination, so 2001:DB8:C000::99. So this example shows 3 route entries, but only 2 of them are valid match. So with one of those being the longest match. So the first 2 route entries have prefix lengths that have the required number of matching bits as indicated by the prefix length. So the first route entry, which is 2001:DB8:C0:00::40. So the prefix length of 40 matches the first or the 40 far left bits in the IPv6 address. So the second one would be a prefix length of 48. So that is 2001:DB8:C00:::/48. Alright. So the second route entry has a prefix length of /48, and with all 48 bits matching the destination IPv6 address, and is the longest match. So the third route, which is not a match because it's /64 prefix. So it requires 64 matching bits. So for the prefix 2001:DB8:C000::5555::/64 to be a match, so the first 64 bits must match the destination IPv6 address of the packet. So only the first 48 bits match. So this route entry is not considered a match. So for the destination IPv6 packet with the address 2001:DB8:C000::/99 or 99/48, consider the following 3 route entries. Alright? So next is build the routing table. So a network or routing table consists of prefixes and their prefix lengths. But how does the router learn about these networks? So let's take a look at this topology here. Okay, so the network, okay, or the presentations that I'm going to do is based on the perspective of R1. Now, referring to the figure, so the networks in the topology are highlighted and labeled from the perspective of R1. Okay, all IPv4 and IPv6 network highlighted in yellow are directly connected. So this network here, 10.0.10/24, is directly connected to R1. This 10.0.20/24 is directly connected to R1 also, and so with 10.0.30/24. So there are 3 subnets directly connected to R1, and these are marked yellow here. Okay, now all the IPv4 and IPv6 networks highlighted in blue are remote networks for R1. Okay, now referring to these networks, 10.0.40/24, you've got 2009.165.200.224/30. You've got 10.0.50/24. Okay, and the internet is, of course, all of these are remote to R1. Okay, so there are also 3 networks or subnets connected to R2. So these are 10.0.40, 10.0.50, and 209.165.200.224. Okay? All right. So different ways a router learns routes. Okay? So basically we have several, or we have 3. Okay, so the first one would be directly connected networks. So directly connected networks are networks that are configured on the active interfaces of a router. So a directly connected network is added to the routing table when an interface is configured with an IP address and subnet mask or prefix length and is active, all right? So up and up on status. Okay? So next would be the remote networks. So remote networks are networks that are not directly connected to the router, okay, as shown in the topology presented earlier. So routers learn about remote networks in 2 ways. So first, static routes. So added to the routing table when a route is manually configured. Second is dynamic routing protocols. So added to the routing table when routing protocols dynamically learn about the remote network. So dynamic routing protocols include Enhanced Interior Gateway Routing Protocol, or EIGRP, Open Shortest Path First, or Ospf, as well as several others. Okay, so the third one would be a default route. Okay, a default route specifies a next hop to use when the routing table does not contain a specific route that matches the destination IP address. So the default route can be entered manually, a static route, or learned automatically from a dynamic routing protocol. So a default route over IPv4 has a route entry of 0.0.0.0 or quad 0/0, and a default route over IPv6 has a route entry of ::/0. Okay, so the /0 prefix length indicates that 0 bits or no bits need to be matched the destination IP address for this route entry to be used. So if there is no routes with a longer match, okay, so most than or more than 0 bits, then the default route is used to forward the packet. So the default route is sometimes referred to as the gateway of last resort. Okay, so let's talk about packet forwarding now. Okay, so packet forwarding decision process. So now that the router has determined the best path, okay, so that is via the longest match or the best match, okay. So the packet based on the longest match So it must determine how to encapsulate the packet and forward it out on the correct egress interface. Okay, so the figure here demonstrates how a router first determines the best path and then forwards the packet. Okay, so the following steps describe the packet forwarding. Okay, and starts or begins with the data link frame with an encapsulated IP frame or IP packet arrives at the egress or ingress interface. Okay, so started with this one. So this one here is a frame. Okay, so you've got data link header, the destination IP address, the rest of the IP packet, and the trailer. Okay, so the data link frame with an encapsulated IP packet arrives on the ingress interface. When I say ingress, that is the incoming. Okay, that's the input. Second, so the router examines the destination IP address in the packet header and consult its IP routing table. Okay, so the router finds the longest matching prefix in the routing table. And then the fourth step would be the router encapsulates the packet in a data link frame and forwards it out the egress interface. So the destination could be a device connected to the network or a next hop router. Okay, so the fifth one would be, however, if there is no matching route entry, the packet is dropped. Okay, so which is the default behavior of a router. So forwards the packet to a device on a directly connected network. Okay, so if the route entry indicates that the egress interface is directly connected network, this means that the destination IP address of the packet belongs to a device on the directly connected network. So therefore, the packet can be forwarded directly to the destination device. So the destination device is typically an end device on an Ethernet LAN, which means the packet must be encapsulated in an Ethernet frame. Okay, so to encapsulate the packet in an Ethernet frame, the router needs to determine the destination MAC address, okay, associated with the IP address of that packet. So the process varies based on whether the packet is an IPv4 or an IPv6. Okay, so for the IPv4 packet, the router checks its ARP table for the destination IPv4 address and an associated Ethernet MAC address. So if there is no match, the router sends an ARP request. The destination device will return an ARP reply with its MAC address. So the router can now forward the IPv4 packet in an Ethernet frame with the proper destination MAC address. Okay? Now, in case of an IPv6 packet, so the router checks its neighbor cache for the destination IPv6 address and an associated Ethernet MAC address. So if there is no match, the router sends an ICMP-v6 neighbor solicitation or NS message. The destination device will return an ICMP-v6 neighbor advertisement or NA message with its MAC address. So the router can now forward the IPv6 packet in an Ethernet frame with the proper destination MAC address. Okay? Alright, so how about forwarding the packet to the next hop router? So if the route entry indicates that the destination IP address is on a remote network, this means that the destination IP address of the packet belongs to a device on a network that is not directly connected. Okay, so therefore, the packet must be forwarded to another router, specifically a next hop router. So the next hop address is indicated in the route entry. So if the following router and the next hop router are on the Ethernet network, a similar process, ARP and ICMP neighbor discovery or ND will occur for determining the destination MAC address of the packet as described previously. So the difference is that the router will search for the IP address of the next hop router in its ARP table or neighbor cache instead of the destination IP address of the packet. So take note that this process will vary for other types of layer 2 networks. Okay? So the third one would be drop the packet. So if there is no match in the routing table, the default behavior of the router is to drop the packet. Okay? So if there is no match between the destination IP address and a prefix in the routing table, and if there is no default route, the packet will be dropped. Okay? So again, the default behavior of the router is to drop the packet if it is not on the routing table, or you have not configured, okay, so the default route or the gateway of last resort. Okay, so the next one would be the end-to-end packet forwarding. So the primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link frame, okay, for the outgoing interface. For example, the data link frame format for a serial could be a point-to-point or PPP protocol, high-level data link control or HDLC protocol, and some other layer 2 protocols like frame relay. Or you also have ATM or the old ones. Okay? Alright, so I have here an example of an end-to-end packet forwarding. Okay? So initially, PC1 sends packet to PC2. Okay, so this is our source here, and our destination is on PC2. Okay, so in the animation, PC1 sends a packet to PC2. Okay, note that if an ARP entry does not exist in the ARP table for the default gateway 192.168.1.1, PC1 sends an ARP request. So router 1 would then reply, okay, with an ARP reply. Okay, so take a look at the animation here. So because PC2 is on a different network, I will encapsulate the packet and send it to the router. Alright, so this packet's layer 3 data. Okay, so that is the first hop, okay, or the first movement of the packet. Now let's take a look at what will happen when the packet reaches R1 going to R2. Okay, now R1 forwards a packet to PC2. Okay, so R1 now forwards packet to PC2. Because the exit interface is on an Ethernet network, R1 must first resolve the next hop IPv4 address with a destination MAC address using its ARP table. So if an ARP entry does not exist in the ARP table for the next hop interface, which is 192.168.2.2, okay, R1 sends an ARP request. R2 would then return an ARP reply. Same thing with the process happened on PC1 and R1. Alright? So it has been forwarded now to the exit interface 192.168.2.1. Okay? Now your packet now is on R2. Now R2 forwards the packet to R3. Okay? R2 now forwards the packet to R3. So because the exit interface is not an Ethernet network, R2 does not have to resolve the next hop IPv4 address with the destination MAC address. So when the exit interface is a point-to-point serial connection, the router encapsulates an IPv4 packet into a proper data link frame format used by the exit interface. It might be an HDLC, a PPP, or any other protocols. So because there is no MAC address on the serial interfaces, R2 sets the data link destination address to an equivalent of a broadcast. Okay? So that is from R2 to R3. Okay. Next would be R3 forwards the packet to PC2 now. Okay. So because the destination IPv4 address is on directly connected Ethernet network, R3 must resolve the destination IPv4 address of the packet with its associated MAC address. So if the entry is not on the ARP table, R3 sends an ARP request out of its Fast Ethernet 00 interface. PC2 would then return an ARP reply with its MAC address. Alright? Next, packet forwarding mechanisms. So as mentioned previously, the primary responsibility of the packet forwarding function is to encapsulate packets in an appropriate data link frame, okay, so for the outgoing interface. So the more efficiently a router can perform this task, the faster packets can be forwarded by the router. So routers supports the following three packet forwarding mechanisms. So these are process switching, fast switching, and the Cisco Express forwarding. So assume that there is a traffic flow which consists of 5 packets. They are all going to the same destination. Alright. Okay, so let's start with process switching. So process switching is an older packet forwarding mechanism still available for Cisco routers. So when a packet arrives on the interface, okay, so it is forwarded to the control plane where the CPU matches the destination address with an entry in its routing table, and then determines the exit interface and forwards the packet to the exit or egress interfaces. Now, it is important to understand that the router does not or does this every packet, even if the destination is on the same network for a stream of packets. So the process switching mechanism is very slow and is rarely implemented in modern networks. Contrast this with fast switching. Alright? Now, let's talk about fast switching now. Okay? So fast switching is another older, okay, packet forwarding mechanism which was a successor of process switching. So fast switching uses a fast switching cache to store next hop information. Okay, so when a packet arrives on the interface, it is forwarded to the control plane where the CPU searches for the match in the fast switching cache. So if it is not there, it is process switched and forwarded to the exit interface. Alright? So the flow information for the packet is also stored in a fast switching cache. Okay? If another packet going to the same destination arrives on the interface, the next hop information in the cache is reused without CPU intervention. So with fast switching, notice how only the first packet of flow is process switched and added to the fast switching cache. So the next 4 packets are quickly processed based on the information of the fast switching cache. Alright? So the last one would be the Cisco Express Forwarding or CEF. CEF is the most recent and default Cisco iOS packet forwarding mechanism. So like fast switching, CEF builds a forwarding information base or FIB, okay, and an adjacency table. So however, the table entries are not packet triggered like fast switching, but change triggered, such as when something changes in the network topology. So therefore, when a network has converged, the FIB and adjacency table contains all the information that the router would have to consider when forwarding packet. So Cisco Express Forwarding is the fastest forwarding mechanism and the default Cisco routers and multi-layer switches technology. So Ceph builds the FIB and adjacency table after the network has converged. When you say converged, this is the state of stability of the network. Okay, so all 5 packets are quickly processed in the data plane. All right. Okay, now let's move on to the basic router configuration review. Okay, so let's have our topology here. A router creates a routing table to help it determine where to forward packets. Okay, so but before diving into the details of the IP routing table, so this topic reviews basic router configuration and verification tasks. All right, so the topology in the figure will be used for configuration and verification examples. So it will also be used in the next topic to discuss the IP routing table. So our topology comprises of several routers and switches with 4 clients connected to it. Okay, so the ISP or the internet is connected via R2 and it might be propagated going to R1. Okay. All right. So basic configuration. Okay. So review. So to configure your routers, so basic setup is necessary. And this basic setup includes something like configuring the host name, okay, enabling the secret password via enable secret your password. You've got line console 0, lagging synchronous, password Cisco login. Now line console 0 is being used, okay, so whenever you want to get into the router for the first time, okay, and prompted you a password, that is the line console 0, right? So line VTY 0 to 4 here, this is being used for remote access. Okay, so there are 5 virtual lines 0 to 4, password Cisco login, transport input SSH, telnet, exit. So when you want to remotely access R1, okay, so from other device or remote devices, the line VTY is in effect. Okay, so this is used for remote access. Okay. The next configuration here is the service password encryption. Okay, so the service password encryption encrypted all the passwords used in the configuration. All right, and then you also have here the banner MOTD. So warning, unauthorized access is prohibited. So this will gives you some notifications. Okay, so but then it's mostly used for legal purposes. All right. Next, for IPv6, this is how we configured IPv6. Of course, we've started with IPv6 unicast routing and then configuring an IP address. So interface Giga Ethernet 0000. So description, link to LAN 1. So IP address, IPv6 address, and of course, no shutdown, right? We have to enable the interface. Okay. So after all the configurations, we have to save it using the command copy run start. All right. So this is the basic configuration of a router. From the basic setup to the IP assignment, okay, and then saving. Now we have some verifications or common verification commands, okay, so which includes show IP interface brief, show run, right? You also have show interfaces, show IP interface, show IP route, and ping. So in each case, replace IP with IPv6 if you want to use the IPv6 version of it. All right. Okay, so using our topology presented earlier, okay, our reference is on R1. Now, when you have show IP interface brief, it will gives us the interface name, right? So the IP address assigned to it. So the status, all right, and the protocol status, all right, if it is up or down. The show IP interface brief. This one is very useful in troubleshooting. All right. So the next one would be show IPv6 interface brief. Now this will gives us all the IPv6 configured interfaces, including the IP address and the status. All right. Next, show run or show running config interface Giga Ethernet 0000. Now this will give us the details or the information about the Gigabit Ethernet 0000. But without this option here, it will show us all the configured information about the routers. Now in this case, this gives only information about the configurations made on the specific interface, which is Gigabit Ethernet 0/0/0. All right. So the show run command will just show us what we have configured on the device or specifically on the interface. Okay. So if you want to get the details of the Gigabit Ethernet 000 or specific interface, so your command should be show interfaces and then the specific interface. Now this would give us, okay, so the status, all right, this one is up. Okay, line protocol is up. You can also see here the IP address assigned, right? So the maximum transfer unit, the bandwidth, the delay, encapsulation, okay? So the duplex mode, and so on, and other information, all right, relates to Gigabit Ethernet 000. Next, show IP interface Gigabit Ethernet 000. All right, so specific information again about the interfaces, okay? So including the technology supported on that specific interface. So something like the Ipv6 switching is enabled, all right? So the MTU is still there, okay? The IP address and the subnet mask is also indicated. Next, for IPv6 version of the command, you could have show IPv6 interface Gigabit Ethernet 00. So this is the same with that of IPv4. All right. So the next one would be show IP route. Okay. So this is the routing table. So basically what you see here are just C and L. Okay. So C means directly connected, and L, basically these are the local IP address, okay, or the IP address connected to the specific interface, denoted by L. Okay. Now displaying the IPv6 route, show IPv6 route displays only the IPv6 equivalents. Okay. And the last verification command is of course ping. Right? So would it be IPv4 or IPv6? We have a simple command or a single command, ping IP address. Okay, so we can also filter the command output. Okay, so another useful feature that improves user experience in the command line interface or CLI is filtering the show output. So filtering commands can be used to display specific sections of the output. So to enable the filtering command, we are using the pipe character, no, after the show command, and then enter a filtering parameters and filtering expression. So this includes section, include, exclude, and begin. Okay. Now section, this displays the entire section that starts with a filtering expression. Okay, so I'm going to give you an example as we progress on this video lecture. Now include, this includes all output lines that matches the filtering expression. Exclude, this excludes all output lines that match the filtering expression. So this is the opposite of include. And you also have begin. This displays all the output lines from a certain point, starting with the line that matches the filtering expression. So take note that output filters can be used in combinations with show commands. All right. So we have here an example. Okay. So show running config. Okay, so pipeline, section, line VTY. So if you will observe, the output should start with line VTY. So if you have several line VTY there, that would be displayed starting on that point, line VTY. Okay, so instead of typing show run, that would display all the configurations made on the device or on the router. So we could simplify, okay, and minimize the output by using this pipeline commands. All right. So another example is show IPv6 interface brief include app. So this will display only all configurations, okay, or all the status of the interface on IPv6, which includes the status app. All right. So next would be show IP interface brief exclude unassigned. Okay, so this will not display any interfaces that are unassigned. So if you want to see only interfaces without the unassigned status or IP address there, which is set to unassigned, okay, in the specific interface, then you could use the exclude. Anything that you don't want to see on the output, use exclude. All right. So next, show IP route begin gateway. Okay. So what will happen is on the routing table, this is, take note, show IP route. So this would display the routing table starting with or beginning with the gateway keyword. So gateway of last resort is not set. So that would give you the output. All right. Now let's talk about IP routing table. Do you know how to read routing table? Let's see. Okay. So let's start with route sources. How does a router know where it can send packets? It creates a routing table that is based on the network in which it is located. So a routing table contains a list of routes to known network. So prefix lengths. Okay, so the source of this information is derived from the following. So again, we've covered already directly connected networks, static routes, dynamic routing protocols. So these three are the sources of the information in the routing table. Okay, so the source for each of the route in the routing table is identified by L, C, S, O, asterisk, and so on. Okay, so for now, let us limit ourselves with these characters here. L identifies the address assigned to the router interface. Okay, so whatever IP address you assigned on that interface or specific router, it will be noted as L in the routing table. Okay, next, C identifies a directly connected network. So basically, your L is just a component of C. Okay, so L is the specific IP address assigned to the interface, and that specific IP address belongs to a network C. Okay, next is S. S is for static route. Okay, O identifies a dynamically learned network information from another router using the Ospf routing protocol. You also have D, okay, for EIGRP. Now, asterisk, this route is a candidate for a default route. Right? Now, in the routing tables for R1 and R2, notice that the sources of each route are identified by a code. So the code identifies how the route was learned. Right? For instance, common codes such as the L, okay, the C, O, and then you also have there the O asterisk or the asterisk. This route is a candidate for a default route. All right. So if you'll observe, C there are the directly connected networks. Okay. So for instance, 10.0.1.0. 10.0.1.0 is this network here. All right. That's directly connected to R1. Another one is 10.0.2.0, which is this network. So take note that we have three directly connected networks to R1. Let us evaluate that. And the third one would be 10.0.30 here. Okay, that's 10.0.30. So we have 3 Cs there. These are the 3 directly connected networks to R1. How about L? L are the IP addresses assigned to the specific interface. So we have also 3L here. This one, which is 10.0.11, right? You've got 10.0.11. You also have 10.0.21, 10.0.21, and the third one is 10.0.31. Okay? Now, letter O here, it means dynamic routes learned from the remote networks or R2. All right? Next, on R2, now evaluating R2 here, okay? So we have 1, 2, 3, 4. Okay? So we have 4 directly connected networks. You've got 1, 2, 3, 4. So usually, the number of directly connected networks is also the number of L you have there. So 1, 2, 3, 4. Okay? Because these are the IP addresses configured on the interface. Okay? So take note that we also have S here. Okay, what is that S? Okay, so the gateway of last resort was configured, so that means the default route was set on this router, and that is denoted by S asterisk there. All right. Okay, so routing table principles. There are 3 routing table principles as described in the table. So these are issues that are addressed by the proper configuration of dynamic routing protocols or static routes on all the routers between the source and destination devices. Okay, so the first one would be every router makes its decision alone based on the information it has in its own routing table. Okay? Second, the information in the routing table of one router does not necessarily match the routing table of another router. And then third, routing information about a path does not provide return routing information. So you have to manually set the return trip, okay, if you are using static. Okay. Now, if it is dynamic, well, let the routers discover all the possible paths, okay, to reach the destination. Okay. So, as network administrator, it is imperative to know how to interpret the content of an IPv4 and IPv6 routing tables. So the figure displays an IPv4 and IPv6 routing table entries on R1 for route to remote network 10.0.0, okay, or 10.0.40/24 and 2001 TB8 ACAD 4::/64. Both these routes were learned dynamically from Ospf routing protocols. Okay, so basically, we have here, okay, so the information available. So the first one, or one there, denotes a route source. So this identifies how the route was learned. And this is via dynamic, since O is Ospf and it's a dynamic routing protocol. So the second one is a destination network. So prefix and prefix length. So this identifies the address of the remote network. So this is your destination network here, going to 10.0.40/24. The third one is an administrative distance. This identifies the trustworthiness of the route source. Lower values indicate preferred route source. Okay, so the level of believability or the level of trustworthiness is the administrative distance. And in this case, this is 110. Ospf administrative distance is 110. All right. Now, at the bottom of 110 is 50. This pertains to the metric. This identifies the value assigned to reach the remote network. So lower values indicate preferred routes. So number 5 is the next hop. Okay, this identifies the IP address of the next router to which the packet would be forwarded. All right, and number 6 is a route timestamp. This identifies how much time has passed since the route was learned. And the last one is exit interface. This identifies the egress interface to use for the outgoing packets to reach their final destination. All right, so take note that the prefix length of the destination network specifies the minimum number of a far left bits that must match between the IP address of the packet and the destination network or prefix for this route to be used. Okay? How about directly connected networks? So before a router can learn about any remote networks, it must have at least one active interface configured with an IP address and subnet mask or prefix length. So this is known as directly connected networks or directly connected route. So routers add a directly connected route to its routing table when an interface is configured with an IP address and is activated. So a directly connected network is denoted by the status C in the routing table as presented earlier. Now the route contains a network prefix and a prefix length. Okay, so the routing table also contains a local route for each of its directly connected networks, indicated by the status code of L. So also, this is the IP address that is assigned to the interface on that directly connected networks, which is L. Okay, for IPv4 local routes, the prefix length is 32, and for IPv6 local routes, the prefix length is 128. Okay, so this means that the destination IP address of the packet must match all the bits in the local route for this route to be matched. So the purpose of the local route is to efficiently determine when it receives a packet for the interface instead of a packet that needs to be forwarded. Okay, so on this output here, show IP route, directly connected networks are denoted by C and L. So the first output here is for IPv4 and the next output would be for IPv6. Alright, so the next one is static routes. So after directly connected interfaces are configured and added to the routing table, static or dynamic routing can be implemented for accessing remote networks. So static routes are manually configured. They define an explicit path between two networking devices. So unlike dynamic routing protocol, static routes are not automatically updated and must be manually reconfigured if the network topology changes. So the benefits of using static routes include improved security and resource efficiency. So static routes use less bandwidth than dynamic routing protocols, and no CPU cycles are used to calculate and communicate routes. So the main disadvantages to using static router is the lack of automatic reconfiguration if the network topology changes. Okay, so static routing has three primary uses. So first, it provides ease of routing table maintenance in smaller networks that are not expected to grow significantly. Second, it uses a single default route to represent a path to any network that does not have a more specific match with another route in the routing table. So default routes are used to send traffic to any destination beyond the next upstream router. And it routes to and stub networks. A stub network is a network accessed by a single route. Okay, and the router has only one neighbor, that's stub network. Okay? Now, in this example, a static route can be configured on R2, okay, to reach the R1 network. Additionally, because R1 has only one way to send out non-local traffic, a default route or a default static route can be configured on R1 to point to R2 as the next hop for all other networks. Okay, so basically the good thing about static routes, this one is secure because you have to manually identify, okay, so the route. Second, this is good for small networks as it uses less resources. All right, but then this is not an ideal solution for an enterprise network. All right. Okay, so static routes in the IP routing table. So for demonstrating static routing, so the topology in the figure is simplified to show only one LAN attached to each router. Okay, the figure shows IPv4 and IPv6 static routes configured on R1, okay, to reach 10040 and 2001 DB8 ACAD 4://64 networks on R2. So the configuration commands are for demonstration only and are discussed in another module. Okay, so the output shows that the IPv4 and IPv6 static routing entries on R1 that can reach 10040/24 and 2001 DB8 ACAD 4://64 networks on R2. So notice that both routing entries use the status code S, okay, when we run the show IP route command there, indicating that the route was learned by static route. Okay, so both entries also include an IP address of the next hop router via IP address. Okay, so the static parameter at the end of the command displays only one or only static routes. Okay, so this is it. All right, you've got S for both IPv4 and IPv6. You've got the destination network, and then you've got the next hop there. Okay, so how about dynamic routing protocols? So dynamic routing protocols are used by routers to automatically share information about the reachability and status of remote networks. So dynamic routing protocols perform several activities, including network discovery and maintaining routing tables. So important advantages of routing or dynamic routing protocols are the ability to select a best path and the ability to automatically discover a new best path when there is a change in the topology. So network discovery is the ability of the routing protocol to share information about the networks that it knows about with other routers that are also using the same routing protocols. So instead of depending on the manually configured static routes to remote networks on every router, a dynamic routing protocol allows the routers to dynamically or automatically learn about these networks from the other routers. So these networks, okay, and the best path to each are added to the routing table of the router and identified as network learned by specific dynamic routing protocols. So the figure here shows router R1 and R2 using a common routing protocols to share network information. All right. Now, in the previous example, we used static routes to the 10040/24 and 2001 DB8 ACAD, right, 4://64 networks. So these static routes are no longer configured, and Ospf is now being used to dynamically learn all the networks connected to R1 and R2. So the following examples show an IPv4 and IPv6 Ospf routing entries on R1 that can reach these networks on R2. Okay, so if you'll observe, it is now denoted by O there, okay, or Ospf. Okay, So notice that both routing entries use the status code O to indicate that the route was learned via Ospf routing protocols. So both entries also include the IP address of the next hop router via IP address. All right. So take note that Ipv6 routing protocols use the link local address of the next hop router. Ospf routing configuration for IPv4 and Ipv6 are beyond the scope of this course. All right. Okay, so the next one would be the default route. A default route is similar to a default gateway on a host. The default route specifies the next hop router to use when the routing table does not contain a specific route that matches the destination IP address. So a default route can be either static or learned automatically from a dynamic routing protocol. So a default route has an IPv4 route entry of 0.0.0.0/0 or an IPv6 route entry of : :/0. So this means that 0 or no bits need to match between the destination IP address and the default route. Okay? Now, most enterprise routers have a default route in their routing table. This is to reduce the number of routes in the routing table. So a router such as home or a small office router that has only one LAN may reach all its network or remote networks through a default route. This is useful when the router has only one directly connected networks and one exit point to a service provider router. So in the figure here, okay, so R1 and R2 are using Ospf to share routing information about their networks. Okay, you've got the 10.0xx/24, and then you've got the 2001 DB8 ACAD-X/64. So R2 has the static route to the ISP, okay, and then R2 will forward any packets with destination IP address that does not specifically match one of the networks in its routing table to the ISP router. So this would include all packets destined to the internet. Okay, so next, R2 has a default static route to the ISP router, and then the default route is advertised by R2 to R1 using dynamic routing protocol Ospf. So R2 has shared its default route with R1 using Ospf. Okay, so R1 will now have a default route in its routing table that it specifically match one of the networks in its routing table to R2. Okay? Okay, so here's the sample output of the default route. Okay, default route on R2, okay, denoted by S asterisk. You've got here 0.0.0.0/0 and a default route also on R2 for IPv6, which is : :/0 there. All right. Okay, so how about the structure of an IPv4 routing table? So IPv4 was standardized in the early 1980s during the now obsolete classful addressing architecture. So the IPv4 routing table is organized using this same classful structure. In the show IP route output, notice that some route entries are left justified while others are indented. Okay, so this is based on how the routing process searches the IPv4 routing table for the longest match. So this was all because of classful addressing. So although the lookup process no longer uses classes, okay, so the structure of the IPv4 routing table still remains in this format. Okay, So although the details of the structure are beyond the scope of this module, it is helpful to recognize the structure of the table. Okay, so as indented entry is known as a child route. Okay, so you'll have this indented, right, on the routing table. So an indented entry is known as a child route. A route entry is indented if it is the subnet of a classful address class A, B, or C network. So directly connected networks will always be indented, okay, or child routes, because the local address of the interface is always entered in the routing table as /32. So the child route will include the route source and all the forwarding information such as the next hop address. Okay, so the classful network address of this subnet will only be shown above the route entry, less indented and without a source code. So the route is known as the parent route. Okay, so this is just a brief introduction to the structure of an IPv4 routing table and does not cover details of the specifics of this architecture. Okay, so if you will observe from the output here, 192.168.1.0 is variably subnetted. Okay, 192.168.1.0 is /24. And under that, okay, so these 4 here are indented. So these are the child or children, and this is the parent. Okay, so that's the structure of an IPv4 routing table. Okay, so in this example shows the IPv4 routing table for R1 in the topology. Notice that all of the networks in the topology are subnets, so which are child routes. Okay, and then these are child routes of the class A network and the parent route 10.0.0.0/A. So all of these are child routes, right? And then you've got the parent route there. Now, how about for IPv6? So the concept of classful addressing was never part of IPv6. So the structure of an IPv6 routing table is very straightforward. So every IPv6 route entry is formatted and aligned the same way. All right. Okay, so next would be the administrative distance. Okay, so from the previous course you have in Cisco, administrative distance pertains to the level of trustworthiness or the believability. Okay, so a route entry for a specific network address or prefix length can only appear once in the routing table. However, it is possible that the routing table learns about the same network address from other than one routing source. Except for very specific circumstances, only one dynamic routing protocol should be implemented on a router. However, it is possible to configure both Ospf and EIGRP on the router. And both running, okay, or both routing protocols may learn the same destination network. So each protocol or routing protocols may decide on a different path to reach the destination based on the metric of the routing table. So this raises a few questions about, or such as the following. Okay, so how does the router know which source to use, or which route should it install in the routing table? Okay, now Cisco iOS uses what is known as the administrative distance or AD to determine the route to install into the IP routing table. So the AD or administrative distance represents the trustworthiness. Okay, so the lower the AD, the more trustworthy. Okay, so because EIGRP has an AD of 90 and Ospf has an AD of 110, the EIGRP route entry would be installed in the routing table. All right, so the AD does not necessarily represent which dynamic routing protocol is best. Now take a look at the table here. So a more common example is a router learning the same network address from the static route and dynamic routing protocols such as Ospf. So a static route has an AD of 1. Okay, so directly connected is of course 0. Alright, so Ospf has an AD of 110. Okay, now when a router has the choice of a static, okay, and Ospf route, the static route takes precedence. So directly connected networks have the lowest AD of 0. Only directly connected networks can have an AD of 0. Alright, so this table summarizes the routing protocols and their associated administrative distance. Alright, so how about static and dynamic routing? Okay, are we going to use static or dynamic? Which one is for us? Okay, now the previous topic discussed the ways that router creates its routing tables. So you now know that routing, like IP addressing, can be either static or dynamic. Should you use static or dynamic routing? The answer is both. Okay, so static and dynamic routing are not mutually exclusive. Rather, most networks use a combinations of dynamic routing protocols and static routes. Now, for static routes, okay, static routes are commonly used in the following scenarios. So, as a default route, forwarding packets to a service provider. Second, for routes outside the routing domain and not learned by dynamic routing protocol. Next is when the network administrator wants to explicitly define the path for a specific network, we use static. And for routing between stub network, we use static. So static routes are useful for smaller networks with only one path to an outside network. They also provide security in larger network for certain types of traffic, or links to other networks that need more control. Now for dynamic routing protocols help the network administrator manage the time-consuming and extracting process of configuring and maintaining static routes. Okay, so dynamic routing protocols are implemented in any type of network consisting of more than just a few routers. Okay, so dynamic routing protocols are scalable and automatically determine better routes if there is a change in the topology. So dynamic routing protocols are commonly used in the following scenarios. So in networks consisting of more than few routers. When a change in the network topology requires the network to automatically determine another path, then dynamic routing protocol is a good choice. And for scalability, as the network grows, the dynamic routing protocol automatically learns about new networks. Okay, now the table here shows a comparison of some of the differences between dynamic and static routing. Okay, so dynamic routing would be good for an enterprise network, so automatically adapts to topological changes. Scalability, well, suitable for simple to complex network topologies. Security must be configured when you use dynamic routing protocol. Resource utilization, well, when it comes to resource utilization, dynamic is high. Path predictability, well, that's the advantage of dynamic routing protocol. Okay, now for static, so the complexity of the configuration increases as the network size increases. So for topological changes, the administrator needs to manually configure, or there should be a manual intervention needed. Scalability, well, static is suitable for small networks. Security is inherent, all right? So no additional resources are needed and explicitly defined by the administrator for path predictability. So it is recommended that we have to use, or we use, dynamic routing along with static routing and vice versa. All right, so let us cover here a dynamic routing evolution. Okay, so dynamic routing protocols have been used in the networks since the late 1980s. Okay, one of the first routing protocol was RIP. RIP version 1 was released in 1998, but some of the basic algorithms within the protocol were used in Advanced Research Project Agency Network, or ARPANET, in early 1969. Okay, now as the networks evolved and become more complex, new routing protocols emerged. The RIP protocol was updated to RIP version 2 to accommodate growth in the network environment. So, however, this network needs to be upgraded, and we have the increase in terms of users and the number of workstations on the network. So RIP version 2 still has not scaled to the larger network implementations of today. So to address the needs of larger networks, two advanced routing protocols were developed. You've got the Ospf and the intermediate system to intermediate system, or ISIS. And then Cisco developed the interior gateway routing protocols, or IGRP, which was then replaced by enhanced IGRP, or we call it EIGRP. So which also scales well in a large network implementations. So additionally, there was the need to connect the different routing domains of different organizations and provide routing information between them. So the border gateway, or BGP, was established. So the BGP, the successor of the exterior gateway protocol, or EGP, is used between the ISPs, or internet service providers. So BGP is also known as the exterior gateway protocol, or EGP. When say BGP, it's either EBGP and IBGP, wherein BGP is popularly known as EBGP. And we have now Ospf version 3 in 1999. And then 2000 onwards, in 2008, you've got ISIS version 6. Next, the table classifies the current routing protocols. Interior gateway protocols, or IGPs. These are routing protocols used to exchange routing information within the routing domain, administered by a single organization. So there's only one EGP, and that is BGP. So BGP is used to exchange routing information between different organizations, known as autonomous systems, or AS. So BGP is used by ISPs to route packets over the internet. So distance vector, link state, and path vector are protocols, so under interior gateway protocols. So basically, from this table, we can classify routing protocols are IGP, or as IGP and EGP. Interior, these are used within the organization, within the control of a single administrator. And EGP is basically used on the ISPs, or among ISPs. Alright? So further, we can divide routing protocols into distance vector, link state, and path vector. So under path vector, you only have BGP there. Link state, you've got Ospf and ISIS. And then distance vector, RIP, and EIGRP. So next would be dynamic routing protocol concepts. So a routing protocol is a set of processes, algorithms, and messages that are used to exchange routing information and populate the routing table with a choice of best path. So the purpose of dynamic routing protocols includes the following. So discovery of the remote networks, maintaining an up-to-date routing information, choosing the best path to destination networks, and ability to find new best paths if the current path is no longer available. So the main components of the routing or dynamic routing protocols includes the following. So it has data structures, okay? So routing protocols typically use tables or databases for their operations. This information is kept in a RAM. You also have the routing protocol messages. Routing protocol use various types of messages to discover neighbor routers, exchange routing information, and other tasks to learn and maintain accurate information about the network. So the next one is algorithm. An algorithm is a finite list of steps used to accomplish a task. That was the definition in programming, right? So routing protocols use algorithms for facilitating routing information and for the best path determination. Okay? So routing protocols allow routers to dynamically share information about remote networks and automatically offer this information to their own routing tables. Okay, so in here, routing protocols allow routers to dynamically share information about remote networks and automatically offer this information to their own routing tables, as shown here. Okay, so routing protocols determine the best path or route to each network. So the route is then offered to the routing table. The route will be installed in the routing table if there is not another routing source with a lower AD. So a primary benefit of a routing or dynamic routing protocol is that the router exchanges routing information when there is topological changes. That's a good thing about it. So this exchange allows routers to automatically learn about new networks and to find alternate paths when there is a link failure to a current network. Okay, how about the best path? Before best path or before a path to a remote network is offered to the routing table, the dynamic routing protocol must determine the best path to the network. So determining the best path may involve the evolution of multiple paths to the same destination network and selecting the optimum or the shortest path to reach that network. So whenever multiple paths to the same network exist, which path uses different exit interface on the router to reach that network. So the best path is selected by routing protocol based on the value or metric it uses to determine the distance to reach the network. So a metric is a quantitative value or quantitative value used to measure the distance to a given network. So the network, okay, or the path or best path to the network is the path with the lowest metric. Okay? So dynamic routing protocols typically use their own rules and metrics to build and update routing tables. All right? So the routing algorithm generates a value and a metric for its path through the network. So metrics can be based on either a single characteristics or several characteristics of a path. So some routing protocols can be based, okay, or can base route selection on multiple metrics. So combining them into a single metric, okay. So the following table lists the common dynamic routing protocols and their metrics. So basically, RIP or the routing information protocol, their metric is based on the hop counts and a maximum of 15 hops, okay, allowed. Next, you've got Ospf. The metric is based on the cost. Okay, so faster links are assigned lower costs. And then the EIGRP, it calculates a metric based on the slowest bandwidth and delay values. Okay, it could also include load and reliability into the metric calculations. So we will be discussing this as we progress with this course. All right. So the animation in the figure highlights how the path may be different depending on the metric being used. So if the path fails, the dynamic routing protocol will automatically select a new path if one exists. All right. Okay, so that's how it works. Next is load balancing. What is load balancing? What happens if a routing table has two or more paths with identical metrics to the same destination network? Okay, so when a router has two or more paths to a destination with equal cost metrics, then the router forwards the packet using both paths equally. So this is called equal cost load balancing. So the routing table contains the single destination network but has multiple exit interfaces, one of each equal cost path. So the router forwards packet using multiple exit interfaces listed in the routing table. So if configured correctly, load balancing can increase the effectiveness and performance of the network. So equal cost load balancing is implemented automatically by dynamic routing protocols. So it is enabled with static routes when there are multiple static routes to the same destination network using the different next hop routes. So only EIGRP supports an equal cost load balancing. Okay, so take a look at this. So our packet traverses going to the destination or same destination using different paths here. Some goes on 52 Mbps top, all right, so that's the first one. And some also uses the 52 Mbps connections between R2 and R3. Okay, so this is what you call load balancing. Okay, so the device or routers uses all the available paths to get into the destination. All right. So that's the end of the video lecture. Thanks for watching and listening. Have a great day.